This is 6.1 homework, counting permutations and combinations. And so in number 1, it says decide whether each object is a permutation or a combination. So let me remind you what a permutation is. Right, a permutation is an arrangement in which the order matters. Right, so order matters on this one. And then a combination, of course, is in a sense an arrangement that is opposite of this, so the order does not matter. So order does not matter. And then down here it has a telephone number. So you ask yourself a question: does the order matter or does it not matter? And a telephone number. And obviously, here the order matters. All right, so we can write down order matters, and so this tells us that this is actually a permutation. Part B is Social Security number. Obviously, the order matters. All right, so this tells us that this is also a permutation. Hand of cards in poker. And so hand cards in poker, the order does not matter. If you had 4 2s and a 5, you could have 4 2s and then a 5, or you could have a 2, a 5, and 3 2s. So the order does not matter. So order does not matter, which implies that this is an example of a combination. A committee of politicians, again, the order does not matter, so this is another example of a combination. A combination to a safe, and so here to be careful. So mathematically, a combination means something differently than in our common jargon for combination. So a combination of safe, certainly the order matters. So we can write down here order matters. And so that means it's actually a permutation. That's how I actually remember the difference between a permutation and combination. I think, well, a combination, the order is supposed to matter, but it's the opposite. So in mathematics, a combination, the order doesn't matter, and a permutation means then the order does matter. A license plate, of course, here the order matters. So that implies that this is an example of a permutation. All right, so that's it for number 1. And number 2, it says use a table to answer the following counting questions when 2 ordinary dice are rolled. Okay, so the idea is you make this table. In this table, what you have on the sides here, you have 1, 2, 3, 4, 5, and 6. And then up here you have also 1, 2, 3, 4, 5, and a 6. And you want to fill this table out. The idea is if possible options on your first die, let's say, possible options on your second die. So you could roll a 1, 1, or you could roll a 2, 1, or you could roll a 3, 1, or you could roll a 4, 1, or you could roll a 5, 1, or you could roll a 6, 1. And then over here, you could roll 1, 2, 3, 4, 5, 6, or a 2, right? So you just keep filling this out. 1, 2, 3, 4, 5, 6. And then you have on the other die a 2, a 2, a 2, a 2, a 2, and a 2. And we just keep on going, so keep filling this out. 1, 2, 3, 4, 5, 6, and this time 3s. And then again, 1, 2, 3, 4, 5, 6. This time 4s. And 1, 2, 3, 4, 5, 6. Now fives. And finally the last one, 1, 2, 3, 4, 5, and 6, and then sixes. All right, so here's my table, and I want to use this table to answer a series of questions. And so how many possible outcomes are there? Well, obviously there's 6 rows and 6 columns, so if you count them all up, you get 36 possible outcomes. How many of the outcomes include a 3? Well, we can use a different color here. So here's a 3. Right, here's a 3. These all include 3s. This one includes a 3, this one includes a 3, and this one includes a 3. Great, so count them all up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So looks like 11 of them include a 3. How many of the outcomes add up to 7? So let's use a different color here. Let's use green. And so you add these up to 2, 3, 4, 5, 6. So this is 7. Go through the next column and you'll see that 5, 2, this one adds up to 7. 4, 3 adds up to 7. 3, 4 adds up to 7. 2, 5 adds up to 7. And 1, 6 add up to 7. And everything else is either less than or greater than 7. So I get 1, 2, 3, 4, 5, 6 of them add up to 7. And that's it. All right, so later on, when we do this, we'll figure out, what's the probability of rolling 2 die when they add up to 7. And the idea will be you'll have 6 possible outcomes. So you could roll 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, or 1, 6. So those are possible ways to get 2 die to add up to 7. And then the total number of outcomes is 36. So the probability is 1 over 6. We'll talk about how you interpret that later. All right, so now let's work with a penny. So a penny is tossed 4 times. And we want to use a tree diagram to answer the following question. So how many possible outcomes are there? So the idea is you toss a penny 4 times. So on the first toss, you could get a head or you get a tails. On the next toss, you have 2 little branches. You get, again, a heads or a tails. So a heads or a tails. And again, third toss, you get a heads or tails here. You get a heads or tails there. Heads or tails here. Heads or tails there. And then the fourth toss, heads or tails. Heads or tails. Heads or tails. Heads or tails. So there's that one. This one also heads or tails. Heads or tails. Heads or tails. And finally heads. Heads or tails. Okay, and so what we want to do next is we want to write down the possibilities for each of these. And so you just go through the different branches here, really. So you start here and you have heads, 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 heads. So heads, 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 heads. Or heads, 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 tails. So heads, 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 tails. Or heads, heads, tails, heads. So you just keep going through this. Heads, heads, tails, heads. Or heads, heads, tails, tails. All right, then you do the next one. So then heads, tails, heads, heads. Right, so heads, tails, heads, heads, or heads, tails, heads, tails. So heads, tails, heads, tails. And again, the next one, heads, tails, tails, heads. tails, tails, heads, or you have heads, tails, tails, tails. And you should get 1, 2, 3, 4, 5, 6, 7, 8 of them. 1, 2, 3, 4, 5, 6, 7, 8 of them. And then you move on to the next branch here. And so now you have tails, heads, 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 tails, heads, heads, tails, right? So I'm moving along here, heads, tails, heads, 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 tails, heads, heads, tails, tails, heads, tails, heads. So tails, heads, tails, heads, and then below it, tails, heads, tails, tails. And finally, tails, tails. So tails, tails, heads, heads, tails, tails, heads, tails. So tails, tails, heads, tails, and then two more. Tails, 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 with the heads at the end. So tails, 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 heads. And finally, tails, 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 tails. And there should be 8 of these. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so we have how many possible outcomes? Well, there's 8 here and 8 here. So a total of 16. How many include at most 2 heads? All right, so let's use a different color. So at most 2 heads. And so now this has 4 heads, so that's too many. This has 3, too many, 3, too many. At most 2, so this has 2. This has 3, that's too many. This has 2, so that's okay. So at most 2 means 2 or less. And this has 2, and this has 1, so that's fine. This has 3, this has 2, this has 2, this has 1, this has 2, this has 1, this has 1, and then of course this has none, so it satisfies the condition. At most 2 means it has 2 or less heads. And so we count them up: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. How many include exactly 3 tails? All right, so let's use a different color here. So exactly 3 tails. So we come down here and we're looking for 3 tails, right? 0 tails, 1 tail, 1 tail, 2 tail, 1 tail, 1 tail, 2 tail. Here's 3 tails. So there's 1. 1 tail, 2 tail, 2 tail, 3 tail, 2 tail, 3 tail, 3 tail, 4 tail. All right, so we want exactly 3, so we get out 4 of them. All right, so count them up: 1, 2, 3, 4. And that's how we use a tree diagram to count things. All right, so this is a bit tedious, and so we want a faster way to do these types of things. And so on the next page, what we're going to do is we're going to use this space method. All right, just use spaces. And we want to write down if the order matters or if the order does not matter. So in a sense, this is an example of a permutation or a combination, really. So on this one, it says, how many different ways can a contest organizer give 3 different awards: first place, second place, and third place, to 100 participants? Okay, so you have 3 awards: first place, second place, and third place. So we can label these if you want: first, second, and third. And you have 100 participants. Now we're going to assume that one participant can't claim first and second, so each award goes to a different person. So you have 100 choices for the first place, 99 choices for the second place, and then 1 less here, which is 98 choices for the third. So to find our answer, we have 100 times 99 times 98, which is equal to, so take out your calculator, and you take 100 times 99 times 98, and you get back your answer of 970,200 different ways. And then, does the order matter here? Well, yes, the order matters. Let's say, take a person like Jimmy. If Jimmy, Johnny, and Joey goes like this: Jimmy, Johnny, Joey, right? If you switch them up, Joey, Johnny, Jimmy, these are different things because the awards are different: first, second, and third. So here, I'd say the order matters. Right, so that's actually an example of a permutation. Now the next problem, part B, it says how many different ways can a contest organizer give 3 first place awards to 100 participants? Okay, so now you have 3 spots, but they're all the same. So the idea is you count them as if they're different at first. So 100 choices there, 99 choices there, 98 choices there. But when you go to compute this, you remember that the order doesn't matter. So you have 100 times 99 times 98, and you're going to divide out by actually, so if you think about this, the idea is if, let's say you just put the guy who has name A, B, and C here, right? This thing, you want to count it as being the same as if you put B here or A here and C here, because they're all first place awards. They don't differ from each other. So we don't want to count these as being different. We want to count these as being the same. Right? That's why we say, in a sense, the order does not matter in this one. So we want to get rid of these things that we're counting, more than once. So we divide out by the number of ways to rearrange, 3 letters basically, which is, 3 choices here, 2 choices there, and 1 choice there. So 3 times 2 times 1. And so if we do this, we can just hit divides by left parenthesis if you want 3 times 2 times 1. And we get a slightly smaller number of ways we can give these awards, which is 161,700. So that's the answer for part B. And part C, what do we have? So in part C it says how many different 7-digit telephone numbers are possible. Alright, so in this one we have 7 blanks, so 1, 2, 3, 4, 5, 6, 7. And if you look on a telephone, there's actually 10 digits, 1 through 0. And so the number of possibilities for the first spot is 10. Okay, the second spot, the number of possibilities is not 9 because we can use the same number again, so we get 10, and 10, and then 10 choices here, 10 choices there, 10 choices there, and 10 choices there, for a total of, let's see, 10 times 10 times 10 times 10 times 10 times 10 times 10, 10 to the 7th. Right, if you put this in your calculator then, right, 10 raised to the 7th, you get back, looks like, what, 10 million? So 10 million ways. And of course, the order matters. All right, so just think about it. You can have, 7 numbers, and if you rearrange the numbers, you're going to get a different telephone number. So here the order matters. All right, on part D, it says how many 5-card poker hands are possible if there are 52 cards in a deck. All right, so a poker hand has 5 cards in it. And of course, you have 52 choices, let's say, for the first card. And you can't reuse that card. It's not as if you can put the card back in the deck and then reuse it because that card stays in your hand. So next one, you have 51 choices, 50 choices, 49 choices, and 48 choices. So you might guess that there are 52 times 51 times 50 times 49 times 48 possible hands, but you'd be slightly wrong because you'd be counting some of these hands too many times. What do I mean? Well, let's just say you have all hearts and you have 2, 3, 4, 5, and 6. All right, the way that we've counted this stuff, then if you switch 3 and 2, right, this would count this hand as being different. And of course, we want these 2 hands to be basically the same. So what we have to do is divide out by the number of ways we can rearrange these 5 numbers. And so, of course, there's 5 spots, so you get 5 times 4 times 3 times 2 times 1. So in this case, you divide out by 5 times 4 times 3 times 2 times 1 to get rid of that sort of redundancy in counting. And so this is equal to, take out your calculator, and you just plug it in, okay? So 52 times 51 times 50 times 49 times 48 times 47, then divided by left parenthesis 5 times 4 times 3 times 2 times 1, in parenthesis, enter, and out pops my answer, which is quite large. Oops, and I made a mistake here. So I need to, that 47 shouldn't be there. So second, enter. Let's go back and just delete that 47. All right, so delete. I should have stopped at 48. All right, so now hit enter, and out pops my answer. That's better. So 2,598,960. So 2,598,960 possible hands. So a lot of different poker hands possible. All right, on the next part, part E, it says how many different ways can 90 children line up single file after recess? All right, so if you go back to elementary school, you remember we lined up single file, and so we have 90 kids. And so the idea is you have 90 spots, so 1 spot, 2 spot, 3 spot. Oh, we should answer up here, right? Remember, the order here does not matter. Okay, then you have the 4 spot, and so on, all the way up to the 90th spot. Right, this is the way the kids line up. And so for the first spot, of course, you have 90 choices possible because you have 90 kids. Then one kid fills that spot, so now you have 89 choices, 88 choices, 87 choices, all the way down to 1 choice. And so the idea is you take 90 times 89 times 88 times 87 times ... all the way down to, 3, 2 times 1. And this number actually is too big for your calculator to crunch, so what we have is a notation that expresses this, and so we write 90 factorial. All right. And this exclamation mark, what it represents is take 90 times 89 times 87 times ... down to 3 times 2 times 1. All right, so there's 90 factorial ways these children can line up. All right, this number is actually too big for your calculator to crunch. All right, so you can write it down in that shorthand form, or just write down it like this: 90 times 89 times 88 ... times 3 times 3 2 times 1. Now here the order certainly matters. Right, why does the order matter? Well, Jimmy's in front. We want to count that different if Jimmy's in back, type idea. All right, so on part F, how many different ways can a 10-member committee be formed out of 30 people? Okay, so again, we have 10 spots, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we want to put 30 people onto a committee, but there's only 10 people on there, so we got to pick 10 people from the 30. So what we'll do is say, okay, well, for the first spot, we have 30. Second spot, 29, right, 28, 27, 26 choices here, 25 there, 24 there, 23 there, 22, and then 21 choices for the last spot. But you have to remember that when we count things like this, we probably counted things more than we need to. So, we take this 30 times 29 times 28 times 27 times 26 times 25 times 24 times 23 times 22 times 21, and then we're actually going to divide out. All right, so pretend like you actually have people here, like you have just one choice. So suppose we label the people A, B, C, D, E, F, G, H, I, J. Okay, the way that we counted these, if we rearrange A, B, C, D, E, F, G, H, I, J differently, we'll be counting that different. But that's not a new committee. It's the same exact committee. So now we have to divide out by the different ways we can rearrange the first, let's say, 10 letters of the alphabet, which, of course, there's 10 for the first choices for the first spot, 9 for the second, 8 for the third, and so on. 7, 6, times 5, times 4, times 3, times 2, and then times 1. All right, so you get to multiply out the top, then divide by when you multiply the bottom, or you could simplify this a little bit and take 30, choose 10. So I talked a little bit about this in class last time, how you can use your calculator to do permutations and combinations. Because remember, this one, right, the order does not matter. And it is a combination. Right, so there's a little button on your calculator, so you pull up your calculator, and if you hit 30, and then you hit second math, oops, not second math, just math, right, then go over to probability, you'll see this button down here, NCR, which stands for combinations, and N is 30, and then you put 10 right here and hit enter, and it's going to spit out the answer. So this one's actually 30,045,015. So this is equal to 30,045,015 ways to make a 10-person committee out of 30 people. Again, you could also just multiply at the top and divide by when you multiply out the bottom. If you do it like that, make sure you put parentheses, though, in the denominator. Okay, last one. All right, so if there is a 10-digit keypad on the safe and the code is 6 digits long, then how many possible codes are there? All right, so the idea is you have 6 spaces, 1, 2, 3, 4, 5, 6. And of course you have 10 choices for the first space. Right? It could be any of those 10 digits. All right, 10 digits for the second, 10 digits for the third, 10 digits for the fourth, 10 digits for the fifth, 10 digits for the sixth. Right? And don't count down because you could use 0 here, 0 there, 0, 0, 0, 0, and you want to make sure you count all those. The numbers can be repeat. And so in this case, actually the order matters. Right, if it's 1, 2, 3, 4, 5, 6, and you reverse it, 6, 5, 4, 3, 2, 1, that's a different combination on the safe. And so the order matters, and the answer is 10 times 10 times 10 times 10 times 10 times 10, so 10 to the 6, which is equal to 1 million. 1 million. Ways. Right? Different combinations. And now if you look back, you'll actually notice whenever we did a combination, right, we're always dividing out by something. And that's sort of a general rule you can use. You know, here's a combination, the order doesn't matter, and so we're dividing out by something. And then again up here, the order doesn't matter, so we're dividing out by something.